It is 2 in the morning on a stretch of track in rural Nebraska. No station, no crossing, no lights, just gravel, steel rails, and a metal box bolted to a pole beside the line. A mile-long freight train roars past at 60 miles an hour, 10,000 tons of steel shaking the ground. The box does not move. It does not light up. Nothing about it suggests it is doing anything at all. The obvious assumption is that this stretch of track is empty and unmonitored, but in the 10 seconds it takes that train to pass, the box has already read every axle, every wheel, every bearing on board. This happens every 15 miles, on every main line, completely unmanned. Most people picture rail safety as a person with a flashlight, walking the length of a train before it leaves the yard, tapping wheels, checking couplers, eyeballing brake lines. That image isn't wrong exactly, it's just decades out of date as the main defense. Here's the problem nobody talks about. A train can leave the yard in perfect condition, pass every visual check a person could reasonably perform, and still be dying by the time it hits mile 80. Friction doesn't show up on a clipboard. Heat doesn't announce itself to a person standing still, holding a flashlight, looking at painted steel from 3 feet away. The real danger was never the broken train sitting in the yard, the one an inspector can catch with enough time and enough patience. It's the train that looks completely fine, moving at speed, quietly cooking itself from the inside, with nobody in a position to notice until it's already too late to matter. Here's what's actually happening inside that wheel. Every railcar rides on bearings, sealed metal assemblies that let a massive steel wheel spin freely around an axle under enormous load, sometimes supporting well over 30 tons per axle depending on what the car is carrying. When a bearing is healthy, friction is controlled, and the heat it generates bleeds off safely through the housing and the surrounding air moving past it at speed. When a bearing starts to fail, that friction spikes, and because the bearing is sealed, the heat has nowhere to go. It builds silently, trapped inside metal that looks identical from the outside, whether the part inside is fine or already failing. No smoke, no sound, no warning light anywhere on the car. If nobody catches it, the bearing eventually seizes solid. The axle keeps trying to spin inside a housing that's no longer letting it move, and something has to give. Usually it's the axle itself, shearing under the twisting load. That isn't a mechanical inconvenience, that's a wheel departing from a train doing 60 miles an hour with 200 more cars behind it still moving at full speed. So somebody built a machine to watch for exactly this, and it's not subtle once you understand it. The box beside the track fires infrared sensors at the wheel bearings as they roll past, angled precisely to catch the housing on every axle regardless of the car's length or configuration. In the fraction of a second each axle is in range, it captures a thermal reading, compares it against both a fixed danger threshold and the temperature of the other bearings on the same train, and flags anything running dangerously hot or simply hotter than everything around it. No person, no delay, just heat, measured on every axle of every car, automatically, every time. Here's the part that should genuinely unsettle you. The failing bearing usually isn't the old, worn-out one intuition points to. Some of the worst hotbox failures happen on cars that were recently serviced, with bearings that look brand new and passed every scheduled maintenance check on paper. The actual cause is often a manufacturing defect or a speck of contamination in the lubrication, something microscopic that does nothing at low speed and turns catastrophic only under sustained load and sustained heat over hundreds of miles, which means the visible condition of a railcar and even its maintenance paperwork tells you almost nothing about what's happening a few inches inside the axle. A car can look pristine, smell fine, roll smoothly out of the yard, and still be building toward failure the entire trip. Now scale this up, because a single train makes the problem enormous fast. A long freight train can run 200 cars. That's over 800 wheel bearings, all under load, all generating friction, all capable of failing independently at different times for different reasons that have nothing to do with each other. No human crew, walking or riding, could physically monitor that volume in real time across a run that might stretch 1,000 miles through terrain with no roads, no cell service, and no way to stop and check by hand without shutting down the entire line behind it. So this isn't a backup layered on top of human inspection, it is the primary defense. The rail network runs thousands of these detectors, spaced along every main line at regular intervals, quietly scanning every train that passes, all day, every day, forming a monitoring grid. Most people have driven past 100 times in their life without ever registering it as anything more than a box on a pole, and the detectors do more than just read heat. Modern units also catch dragging equipment hanging low enough to strike the rail, measure the impact force of a wheel that has gone slightly out of round, and in some systems, listen to the acoustic signature of a bearing to catch a failure pattern developing before heat even becomes a factor. None of this data stays local. The moment a reading crosses a danger threshold, it transmits instantly to centralized rail traffic control, sometimes hundreds of miles from where the train physically is. A single overheating axle on a remote section of track with no crossing, no town, and nobody watching can trigger an order that stops that train dozens of miles down the line before the crew in the locomotive has any idea something is wrong with the car they're pulling. This is where the story turns genuinely counterintuitive, because what happens next isn't what instinct would suggest. If something on board a vehicle is overheating, the ordinary human reaction is to ease off, slow down gradually, buy a little time to assess how bad it really is. That is not what rail crews are trained to do. When a hotbox alert comes through, the protocol is to stop the train immediately and completely, right where it is, even in the middle of nowhere, even if it blocks other traffic for hours, even if the eventual physical inspection finds the bearing running only slightly warm and otherwise fine. From the outside, that looks like overkill. A fully loaded freight train is expensive to stop and expensive to get moving again, and false alarms happen constantly, caused by nothing more than a warm summer day or a sensor slightly out of calibration. But the math holds because of what sits on the other side of the bet. A wasted stop costs time and fuel and a delayed schedule. A missed failure costs a derailment, and derailments caused by failed bearings have historically been catastrophic, sometimes fatal to crew, sometimes environmentally disastrous when the cargo happens to be fuel, chemicals, or anything else that shouldn't end up spilled across open ground. The system is deliberately built to absorb thousands of unnecessary stops in exchange for catching the one failure that actually matters. That trade-off didn't come from a cautious boardroom sitting down and deciding to be careful. It came from wreckage. Through much of the 20th century, hotbox failures were one of the leading causes of freight derailments in North America, and for decades the only defense was a worker walking past a stationary train, holding a bare hand near the wheel housing, feeling for heat through a glove, which is about as reliable as it sounds and completely useless once the train is already moving at speed. A string of serious derailments traced directly back to undetected hot bearings, including incidents that damaged track, spilled cargo, and in some cases cost lives, finally forced the industry's hand in a way that voluntary caution never had. Regulators didn't introduce automated wayside detection as a proactive improvement dreamed up ahead of the problem. They mandated it after the fact and set specific rules for how far apart these detectors had to be placed along a route, because the pattern of missed failures had become impossible to explain away as bad luck. The technology to detect a hot bearing existed years before it became standard. It took burned rail cars and a public reckoning with the death toll to make it mandatory rather than optional. Once you know this, the trackside world stops looking empty. Those unremarkable metal boxes people drive past their entire lives without a second glance aren't signal equipment or utility housings for some unrelated system. They're detectors, actively reading every train that passes at the exact moment it passes. That strange, oddly specific radio broadcast some rail fans have picked up scanning frequencies near the tracks. A flat, automated voice reading out something like axle count and no defects found isn't random chatter or some leftover military transmission. It's the detector itself, reporting its findings live to the crew sitting in the cab, so they know within seconds whether their own train just passed clean. And the mysterious stops freight trains sometimes make in the middle of open country, with no station, no signal, no visible reason for a driver waiting at a nearby crossing, aren't scheduling quirks or crew breaks. They're often a heat or vibration threshold, quietly getting crossed a few miles back, triggering a stop nobody outside the system will ever be told the reason for. None of this is flawless, and it's worth being honest about where the system still strains under real-world conditions. Dust, extreme weather, and sensor drift can all cause false positives, or worse, missed reads on a genuinely failing bearing, which is exactly why no single detector along a route is ever trusted alone. Corridors are built with multiple detectors spaced along the same stretch specifically, so a developing problem shows up as a rising trend across several consecutive readings, rather than as one anomaly that might just be noise from a hot afternoon. Coverage isn't uniform everywhere either. Older branch lines and lower traffic routes, especially in parts of the world without North America's density of freight traffic, can have far sparser detector spacing than a busy main line, which means the safety margin isn't identical across the whole global network, even if the underlying physics of a failing bearing is exactly the same everywhere. And even with all this automation working exactly as designed, a human being still makes the final call. The system flags a problem. A dispatcher or a crew member decides, based on the full picture in front of them, whether to stop completely, roll to the next siding, or continue on, because the machine can measure heat, but it can't weigh every operational trade-off on its own. So the next time a freight train grinds to an unexplained halt in the middle of nowhere, or a small unlit box flicks past a car window at a level crossing without a second thought, that image should mean something different now. It was never empty track. It was an invisible act of surveillance, protecting a system that moves an enormous share of a country's goods across a network with almost no one physically watching it happen in real time. The whole design only works because it's meant to be forgotten, unnoticed by everyone except the one train it's quietly checking, until the one moment it isn't. And trains are far from the only machines quietly checking themselves like this while the world drives past without noticing. Bridges flex under sensors wired directly into their steel, measuring metal fatigue building up in ways no eye could ever catch from the road. Pipelines listen to their own internal pressure for the faintest whisper of a leak long before it becomes a rupture anyone can see, which raises an uncomfortable question for the next time a loaded train rolls across a bridge in the dark. What if the bridge underneath it is running the exact same kind of silent check on itself, right at that moment, and has been the entire time, waiting for the one reading that finally means something?